Hello, everyone. Welcome to our calculus lectures. This is Calculus 1. And let me begin with a preview of differential and integral calculus. Okay. The objectives to this section is that we will preview the tangent problem by using secant lines from average rates of change. And we will also preview the area problem by using rectangles to approximate area. Let's first understand what calculus itself means. Calculus is a Latin word that means a small stone or a pebble. Interesting, isn't it? Calculus is technically the mathematical study of change. So the focus is on finding the instant rate of change and on the accumulation of areas. So what does it mean? Well, let me put it out here. If I were to I hope you can see what I'm writing. Okay, calculus can be broken into or divided into two prominent areas of study. One is called the differential calculus, and the other is called the integral calculus. So in a differential, the main focus is studying about the instant rate of change. Okay, and for that we kind of use the idea of tangent. So let me write here tangent problem. Okay, and under integral calculus, our focus is in understanding the accumulation of areas. So we call this the area. Area problem. How do we approach this? Well, the good news, the comforting news is that every concept in calculus has its foundation in algebra, and that too simple algebra, all right, and trigonometry. So when we talk about the tangent problem, for instance, when we look at the tangent issue, what we understand is in algebra, we have learned about rate of change, isn't it? Rate of change in algebra, we learned it under the idea of slope, right? Slope of a line. So let's take a look at this example here. What we see here is the first graph here gives us the time in seconds versus the distance traveled. So let's assume this was a car that was traveling, and that's the distance for a given time. Okay. So for instance, if it was 2 seconds into driving, the car traveled a distance of say 6 meters because it's measured in meters, right? So we kind of understand that diagram, the graph. In algebra, we spoke about lines. They're all straight lines. So these lines could be slanted, horizontal, vertical. But when we were interested in rate of change, we were mostly looking at slanted lines and wondered how the slope behaved. And what's nice about lines is the slopes are steady. The slope is the same everywhere between any 2 points on the line. Slope is nothing but the slantness of a line. But then we learned that, well, in real life, we can't always have straight lines. The shape can be a curve. So in this blue graph, you see the curve. And then what algebra taught us was, well, we could take any 2 points on that curve. The 2 points could be the point of interest that we want to focus on. And if you draw a line through it, then you could find the slope of that red line, right? And that was used as an approximation for the rate of change. So in this case, let's say the rate of change of interest was here, right? Between 1 and 3, okay? So I should have used a different color. Okay, between 1 and 3. So you are trying to find the rate of change between 1 and 3. So you're only trying to give an average rate of change um, as per algebra. So this, let's say, this red line, right, is called the secant line because you're trying to connect the two dots on the curve through this line. It's called the secant line. And if you can find the slope of this line, you know it is the rise over run, right? Rise over run. Well, that is algebra. You take the same idea, but then you move into calculus and we're saying, hey, I am interested in finding the rate of change at this point, at this instant, when it's 3 seconds, what is the rate of change? So this now becomes a question of finding the slope of a line at a point instead of between 2 points, right? And so this line is called the tangent line because a tangent, right? Tangent, tangible, touching. So this line touches the curve at that point. So there is a single point that's common to the line, the red line, and the blue curve. And so it's a tangent line that helps us to find the instantaneous rate of change given that particular point, at that point. So, well, this includes the idea of limits, and then we use the process of derivatives to understand this one, this idea of tangent line. Okay, the formal definition will involve limit, and that's where the study of calculus actually begins. So to kind of give you an idea of you know, how we were looking at this or how we developed this idea in one moment here. I'm trying to pull a different color. Okay, here we go. So rate is the rate of change, right? The rate was difference or change in the distance. You know, the delta is a symbol. This triangle is called delta, and that's a symbol to indicate change or difference. So change in distance over change in time. Okay. Yeah, rate or speed is the distance over time, but when we talk about average rate of change, then we're talking about the difference in the distance over difference in time. So for this secant line here, right, average rate of change, I hope you like the music in the background, is the slope of the secant line. Do we agree with that? Yes, because the formula for slope can be applied here, right? And that is m equals y2 minus y1 over x2 minus x1. On the other hand, this side in calculus, we are not talking about the average rate of change. We are talking about the instantaneous rate of change. And that is the slope of the tangent line. And then in calculus, we'll develop into that idea, but if you can kind of see the difference, we're still finding the same slope, but then we use the concept of derivatives, which basically comes from the definition of slope. But then I will find the derivative of the function at 3, because that is the very instant we are interested in, as opposed to this interval of 1 to 3 seconds in algebra. Here we're talking about the particular instant 3 or particular instant 2, just depends on what you're interested in. And that is the general idea of the tangent problem, where it is addressed. If I can take you back here, this is the tangent problem here, and this problem is addressed through differential calculus, and that's what we're going to learn. And now we'll move on to the area problem. In this area problem, let's consider again the blue graph, the first one that you see here. And here again, we are talking about, let's say this models a car that travels for a given time. and it's measured in meters, the distance. However, you notice that the y-axis is not is not measuring the distance, it's measuring the speed. It shows meters per second, right? Meters per second. So that is already giving us the speed. All right, so if we want to know what is the area under this blue curve, okay, area under this blue curve, then we would try to understand that the area under this curve would be, if you could shade the whole region, then we have to figure out how to measure it. So in geometry, what we did was we could use the idea of rectangles to kind of construct rectangles that touches the curve as best as possible, and then try to count how many rectangles there are and try to measure the area, because the rectangle kind of gives a coverage of the area, right? So we could do that. And what happens is you are, there are times when your focus is to find the area below the curve, but because you're constructing rectangles, you won't be always able to build rectangles perfectly under the curve. Sometimes they will go above the curve. So it is an estimate, it's an approximate area. So there are times when you will underestimate and times when you will overestimate, but that is unavoidable because you want to get rectangles, otherwise you'll have chopped rectangles. And how do you measure chopped rectangles, right? If it is not a rectangular shape, you can't use geometry, which tells us that we could find the area of a rectangle by multiplying the length and the width. So we need that shape, and therefore you see that there are some compromises, right? Some spaces that are not accounted for, some spaces that are over accounted. Well, calculus takes care of that issue, and it actually helps you to get the perfect area under the curve, despite the irregular shape that you see coming from the curve, isn't it? So these are not geometrical shapes. So you see these curvy patterns, but we can still use calculus to come up with that area perfectly. So how does this work? Well, for the blue curve, let me say, we would have found the distance. Oh, by the way, the area under the curve actually gives you the distance, right? So we have distance as rate times time, right? So you're trying to find the same distance, but here you are finding the approximate distance. The approximate distance is found by getting the sum of the areas of the rectangles. You can kind of see, three broad rectangles here, right? Let me just try to shade it for you. So you see, this is one rectangle. You can measure, right? You can find the length. The length is going all the way from 0 to 6. So the length is 6 times the height, or in this case, the width. The width is from 0 all the way up to 2 on the y-axis. So 6 times 2 is 12. So you know the area for that first rectangle is 12. Then you will find the area of this rectangle, right? And then you can find the area of this rectangle. So get the areas of each of these rectangles and then add them up. That gives you an approximate area. That's what we're trying to do in algebra. When you move to calculus, well, you're able to give the exact distance. And for that, we use a special symbol, but basically it is coming from the idea of geometry, where when you add up the rectangles, you get, we talk about a concept called Riemann sum. And then from that, we develop into this special notation. We call it the integral notation. And you want to measure the area under the curve over the region from 0 to 18. So 0 to 18, and it is under the curve. The curve is denoted by the function f of x, tx. And this will give you the exact distance, and that is remarkable, right? And that is the whole idea of the area problem, which deals with integral calculus. So we'll look at some examples, but this is the general idea of calculus. So I'm going to quickly move us back to here. And this was the area problem that would be addressed by integral calculus. So let's take a look at this first example related to the instantaneous rate of change, but we're not there yet, so we're going to find the average rate of change. Just a refresher of what we did in algebra. All right, you know that the formula, the slope formula, right? Let me write that out here. Slope formula is y2 minus y1 over x2 minus x1, right? Now, if you had the coordinates given to you, not fully, but just the interval for x, then we could use the secant formula. This is the same as secant. So we put the suffix sec, secant, to say this is the slope of the secant line, not the tangent line, right? Slope of the secant line. And is given to you as f of x minus f of a or x minus a. That's the same thing as y2 minus y1 over x2 minus x1. All right, so you could also modify this, okay, and say, well, that's f of x2 minus f of x1 over x2 minus x1, right? Because you know, if you wanted to make it look very similar to the y2 minus y1 over x2 minus x1, all I did was change the y2 to f of x2 because you have defined it as a function. So what we could do then is, this is x1, right? x1 is -3, and this is x2, because on the number line, x1 is smaller than x2, so you want that to be the first one and this to be the, so you can see from x1 to x2, right? And that would be meaningful when we talk about the slope of the secant line. All right, now let's find, we need to just plug these in our formula. For that, we need to find f of x1, we need to find f of x2, and then we're ready to plug them in. So let's find f of x1. In this case, that's f of -3. You have the function here, right? So I recommend that wherever you have to substitute, please enter parentheses so that you know that that's where you're going to plug in for -3. And remember that it's -3 inside the parentheses, so you may have to be really careful about how the signs combine. So we now have -3 in the parentheses, so we're going to be very careful about how we combine them. So -2 times 9 minus 9 plus 4. You do all the calculations. That gives you -23. Now let's find f of x2, which is f of 2. Do the same thing. We call them shells. I call them shells. So put these shells wherever you have to substitute. Don't be in a hurry to do them all in your head. It's okay when you feel confident to do that, but when you're substitution, don't do substitution and computation in the same step, is my recommendation. Okay. Well, this reduces to do the math. You can pause the video at this point and you could do the math, and that gives you a 2, right? Need more space, so let me insert more space. All right, so now I have f of x1 and f of x2. Now it's time to put it in the formula. Okay. So because x2 comes first, you need to plug in the 2, right? F of 2 minus f of -3 divided by -2 minus -3. Okay, we have learned this in algebra. When you're trying to find the slope, it really doesn't matter which one you consider x1, which one you consider x2. That is really, won't make a difference, because you just will have the corresponding order matched in the formula. So say if I did x1, f of x1 minus f of x2, then the bottom would be x1 minus x2. The signs would be would nullify that effect. So just make sure that you have the same order preserved. If you started with x2 on the top, it should also be x2 in the bottom. All right, so I have 2 minus negative 23 over 2 plus 3, right? And that implies I have 25 over 5, which is 5. So then you can come back and conclude and say the secant line that connects these points, right? These points are the negative 3 and the 2, has a slope of 5. Yeah. How about the next one? Okay, you can again pause the video at this time and try to see if you can race ahead and get this done. For you to be able to come back and verify the answer, I'm just going to present the answer here. So in this case, again, I'm keeping it very similar. So f of negative 3. You know, the x's are the same like the previous problem, but notice your function has changed, so you're not going to get the same answer. So negative 3 times this comes out as negative 26. Okay. And that comes out to be negative 1. For variety, I'm trying to show you that if I chose, let's say here, if I say chose this as, say, x2 and this as x1, okay, it's there is no problem if you move them around like that. Right? So then that will be f of negative 3 minus f of 2 over negative 3 minus 2. Yeah? All right, so we now have negative 26 minus negative 1 over negative 5. This gets interesting now because the answers very interesting. It's a different problem, but we have negative 25 over negative 5, which is 5. So in this case, it's a different function, but it gave us the same answer. It's just a coincidence. It's just to, just for fun. The secant line has the slope 5. Yeah. So feel free to explore other similar examples in this concept. Let's take a look at this problem. Estimate to the nearest whole number the instantaneous rate of change of the function, that's the function given, at x equals 2, using the average rate of change over the interval. Ooh. So we are trying to find instantaneous rate of change, which is the actual calculus question, right? But we're going to use average rate of change, the concept we already know, to compute this, okay? So this is your interval, 2 to 2.01. So you can see what a small interval that is. Because you're trying to find the instantaneous rate of change at 2. So you have to keep your interval really, really close to 2 so that your estimate is stronger, right? It's closer to the true value. So here again, it doesn't give you explicitly what is x1 and x2 because the focus is on just 2. But remember, we are using the average rate of change, so you need 2 points, right? So go ahead and find f of 2.01. So in the given function, okay, that gives us 2.99. Next, we find f of 2, which is x1, right? 2 is x1. Same function, plug in 2. It's touch screen, so I think I'm touching all other features or apps. So if you feel like there is a blank space that comes up or other things that are shared, I apologize. All right, this comes down to 3, okay? I'd like to divide this page so that we could, yeah. Okay, m secant is f of 2.01 minus f of 2 all over 2.01 minus 2, yeah? So that's 2.99 minus 3 divided by 0.01. That comes out to be a -1, okay? So remember, we are trying to find the instantaneous rate of change at x equals 2. But what we found was between 2 points, not at 2, but between 2 and 2.01. So we can kind of see that the average rate of change is approaching, notice the language, is approaching -1, right? So this is the language we will begin to use when we talk about the concept of limits, approaching, right? So we have -1 there. And so, I mean, they said to the nearest whole number, so we got that. So the instantaneous rate of change at x equals 2 is approximately -1. All right? So we saw 3 examples under the tangent problem that involves the concept of differential calculus. Now let's go to the area problem and look at some examples there. All right, look at this graph. This graph is a parabola, as you can see, and it's defined to be f of x as 2x squared plus 2. It says use the given rectangles to estimate the area between the x-axis and the graph of the function. Use the rectangle. So they've shaded this for us. So we're asked to use geometry. Remember, this is area, right? So we're using geometry to find the area under the curve up to the x-axis. So between the curve and the x-axis, basically, right? So here again, if you are trying to construct rectangles below the curve, you may not get complete rectangles in some cases. Therefore, the rectangles given to us here are actually an overestimate. They go above the curve, which is not ideal, but it has to go above the curve in order for us to construct the rectangle and get a complete rectangle. All right, let's focus on this question. Although the graph goes indefinitely, right, because it is a polynomial, it goes on. We are asked to focus only between 0 and 2, right? So this is our focus in this interval, 0 to 2. So here we have the green rectangles, and we're just simply going to find the area of these rectangles and then add them up, okay? So what we'll do is, let's say, let me try and shade this for you. I would like to focus on this rectangle here. I'm kind of chopping this up into two rectangles so that, the whole idea is to add them up, but try to add them in a way that is of minimal computation. Okay, so for this blue shaded region, right, if you look at, this is where it ends, right? That marking is 1, right? That is 1. Because each box here, each square is half a unit. So if you are focused on this rectangle here, then that is, I'll say blue. Blue rectangle has to have length times width to find the area. I'll say area of blue rectangle. So in this case, the length here is 0 to 1. So the length is 1 unit. And the width in this case is the height. Sometimes, you know, the book also calls them as base times height. Instead of length times width, it says base times height. It's the same thing. The base here is 1 and the height is 4. It goes all the way from 0 to 4. So that's 4 units square. Okay. I'm trying to put the S there. Unit square. Okay, next go to the this rectangle here. I'm shading it in pink. Okay, you get the idea, I suppose. Okay. And here, again, look at, let me call it the pink. This is the closest to pink. Area of the pink rectangle. The area formula never changes. It's still the length times width formula. But here the length, again, go back and measure. This is from 1 to 2. So 2 minus 1, right? That's the length, or in this case, the base. So that is also 1 times, look at the height. It goes all the way from 0 to 10. So 10. So that is 10 units square, or square units, you can say. So we want to add the blue and the pink. Four plus 10, which is 14 square units. What we have done is we have approximated the area by adding the rectangles. You could have added it in so many different ways, right? For instance, you could have taken this, how do I show this to you? Okay, you could have done this, right? This whole thing. You could have found the area of this whole thing and then added it to the area of this one, just this part, yeah? So we could have done all those things and you would still get the same value. Just remember what each square is measured so that you will do the correct calculations to measure the units, right? So this is again estimate. And remember, this is the idea that leads up to the calculus concept of integral calculus. Well, let's look at this one, another one. Go ahead and read the problem. The function is given to be negative 1/4 x squared plus 4. Well, it's a parabola that opens downwards, and you can see that. And here again, they have shaded the rectangles for us. So again, for convenience sake, let's focus on this taller rectangle first. And I'd like you to look at the distance, right? The base, the length. So the length is, let's say, length here is 2 because it goes from 0 to 2. And the width here is 0 to 4, right? For the first one. For the second one, the length is from 2 to 4. So 4 minus 2 is 2. And this width goes all the way from 0 up to this point. So make sure what this point references to. So for that, you need to understand how each box is measured, right? From 0 all the way to 2, you have to cross 1, 2, 3, 4, 4 boxes, right? So each box or each square measures half a unit. So this is half, so this must be 1, 1.5, 2, 2.5, so this must be 3. So this position is 3, so the width is all the way from 0 to 3, right? So we have 2 times 4, the area, total area is 2 times 4 plus 2 times 3, right? That gives us 8 plus 6. So our total area is 14 square units. Yeah. All right, so that was just the preview into the concept of calculus and how we try to understand calculus through algebra and geometry, because the focus is on finding the instantaneous rate of change and accumulation of area. I hope you enjoyed this video. This was kind of slow to kind of ease you into the concept. We will run into more serious concepts of calculus in a fun way next lecture onwards. So thank you, and I will see you shortly.